So let's get to what about more general sets, things that aren't mathematically constructed, maybe things that we find in nature. This sort of suggests that we already know. What is the length of the coastline of Great Britain? We're sort of suggesting there, well, this is the coastline of Great Britain is one-dimensional, right? The idea here is if you use different rulers, different ruler sizes, you'll get different numbers. So if I used a 100-mile ruler and just sort of put it on the map of Britain, I'll count so many different 100-mile rulers, somewhere between 18 and 19. So I'd say, oh, it's 1870, 1,870 miles. Now, if I divide that by half and look at a 50-mile ruler, well, I'm going to get a different number. Now, what if I cut that in half, look at a 25 mile, 12 and a half, all the way down? Am I actually going to converge to something? And no, no, you don't. You don't. This keeps on going. So the coastline of Great Britain has infinite length, which should make real estate agents really happy. There's plenty of room for oceanside property, right? So there's something wrong with this. You can't build infinite houses, but of course houses have a certain scale, and we're talking about kind of going with a smaller and smaller ruler, as you get down to the level of pebbles. And of course it's not actually going to be infinite. There's going to be atoms. So at the level of atoms, okay, this is going to converge to something that's very, 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 very long. And of course, it still bounds something of finite area. There's this cool thing with if you take the Koch curve, but then do additional copies and bring them back on themselves, you get what's called the Koch snowflake. So it's a similar construction. It's the Koch curve, but kind of wrapped around. And just like the Koch curve, the boundary of the Koch snowflake is infinite, but it encloses a finite area, just like the coastline of Great Britain. So it seems like the coastline of Great Britain is a fractal and it has some dimension. So how do we get at that? That's where this idea of what's called the box counting dimension showed up. And so we don't mean it's like self-similar, but we've got this effect that the smaller and smaller our ruler, the larger and larger this seems to get. It looks like a fractal in the sense of it's a dimension between 1 and 2. So I don't mean if you were to infinitely scale down, and I don't know if you've seen this, this GIF, infinitely zooming in. I don't know who made this, but it's a very frustrating thing to watch. Like, this isn't what we mean. We don't mean it looks exactly the same. We keep hoping that this will end, but it doesn't. It's an endless coastline. So to answer this kind of question, we can introduce a box counting dimension. So the idea of a box counting dimension is that if you have let's say that curve that I showed up above, if I were to use rulers of a certain length, or you could also equivalently think of it as boxes. If I've got boxes and they each have a length of epsilon, well, this is going to be covered by so many boxes. So for a box or ruler of scale epsilon, I need n boxes to cover that length. And for an actual curve, if we know that the length is L, this thing is going to be proportional to L over epsilon. Now, what about for an area? If I've got an area, there's some area, and I don't mean just the boundary curve, I mean the area inside. If I were to just count the boxes that this touches, I guess it touches that box, this one, touches quite a few, actually. I'm just getting the boundary boxes because those are the difficult ones. So all of these have a scale epsilon. What I'll find is that if this region has an area A, that the number of boxes that I need of the scale epsilon is going to be proportional to A divided by epsilon squared. So if I shrink my boxes in half, right, I would need 4 times as many boxes. Whereas to measure this curve, if I shrink my boxes in half, I'll just need twice as many boxes. So based on that, we might observe that there's this power law going on, so that the dimension of the set equals the exponent d in the power law, the number of boxes at the scale epsilon that I need to fully cover this goes as 1 over epsilon to the d power. Now this power law also holds for fractal sets, except that d is no longer an integer. So how do we define d? It's d is, you look at the limit as epsilon goes to 0 of the natural log of n epsilon. So the number of boxes you need to cover the set divided by natural log 1 divided by epsilon, if you get a limit. So this lends itself to computation. So you could compute this for any given set, including the coastline of Britain. Let's say right now we through some digital elevation map or something, we've got the coastline of Britain down to a scale of 1 millimeter. I doubt we do. I don't know. Google Maps seems to round things off, at least on the scale of like 10 meters or something. But you could at least go down to a pretty small scale, and you could look at if you would plot the number of boxes you need versus 1 over epsilon, the size, and look at the slope. So that's how this is often done. So you could do this for actual things. If you try to calculate it for the Cantor set, you'll find the same thing.
Dr. Raj,
Yeah.
I'm curious, how do we define like the concept of a box if you were to end up like going to like 3 dimensions or like something that could be shown in 3 dimensions, like a, I don't know, some 3-dimensional potato? Would it just become like a cube then? That's what our box would be?
Yes.
And then
yeah, so by box, I mean we might say whatever the embedding space is that you're using. So this should work even if you had a curve in 3-dimensional space. You could use cubes to measure it, but it's still just going to be linear in the cubes.
So the like cube of dimension of the embedding space is what you would use as a box.
Yeah.
Perfect. Thank you.
And epsilon always just means the like length scale. So we wouldn't say epsilon is the volume. We'd say epsilon is just one of the lengths of the sides.
Got it. Thank you.
There's this object that I don't know if it's just a computer drawing, but I'm pretty intrigued by it. It's absurd, but it's called the fractal cow. So I don't know if this is something just a computer graphics or if somebody has 3D printed this. It sort of is a ridiculous illustration of this self-similarity, right? On the cow, you add 7 more cows, and you do that ad infinitum. I don't know what the dimension of this is. I guess just think of the surface. Fractal cow. What is the dimension of the fractal cow? Well, I guess we could use the box counting approach. I haven't, but this has been used for other things. There's an interesting 2-dimensional version of the Cantor set. And again, this is a mathematical construction. But if you were to start with a solid triangle, and then you remove the middle fourth of the triangle. So now we've got something that looks like this. And now apply that procedure again. For each of these, you remove the middle fourth. And hopefully you get the idea. You just keep doing this. But you get something. And you could use the box counting approach. This one is probably computationally tractable that you could analytically get it, but you could estimate it using a box count. You get a fractal, and you get something that'll be with dimension between, because we mean the actual solid area, whatever's left. It'll be between 1 and 2, because we keep removing area. Eventually, this thing has no area, but it's also more than a curve. So what is it? And we could calculate using box counting this, the Koch snowflake, and also the coastline of Britain. All of those you can compute with the box counting dimension for those various objects. For the Koch curve, we actually analytically had calculated it, but now we can also see that compared with some other objects. This thing, right, you take it to its infinite limit, you get something that's 1.585 dimensional. The coastline of Britain, so people have computed this using box counting, and you get something 1.2. Okay, interesting. I mean, these are just ways of characterizing these unusual objects. It's not the only way. There are others, and you might be wondering, well, what about the attractors that we care about? How about those? There's this other way of counting. I guess I should say the box counting dimension is also called the capacity. I'm not sure why, but there's another approach, the correlation dimension. This approach is good when you have calculated something and you have what appears to be a cloud of points. So it's good for the results of calculations from nonlinear dynamics. So if we had some kind of weird thing, let's show a weird thing. So this thing called the correlation dimension. If we have a point, let's call this point X, and we've got a ball. In this case, let's think maybe this is just in 2D. So we have a ball of radius epsilon. So again, epsilon just represents a length. We've got a ball of radius epsilon. We can let nx epsilon denote the number of points inside the ball. So inside a ball of radius epsilon centered at x, the point x. So you could think of nx epsilon, if this was the result of points sort of going onto an attractor, either from a map or from an ODE, and you've discretized in time, this nx epsilon measures how frequently a typical trajectory visits an epsilon neighborhood of the point x. Now vary epsilon. As epsilon increases, right, the number of points in the ball typically grows. Okay, so vary epsilon, and the number of points in the ball grows. The number of points in an epsilon ball centered at x will grow proportional to epsilon raised to the d. At a particular point, this is called the pointwise dimension at x, and it could depend significantly on x. So if we want to know something about the overall, some structure, an attractor, let's say, then you'd want to average over x. So for an attractor A, you want to average nx epsilon over many x points. And when you do that, the resulting quantity is called C epsilon. And this is found to also go as epsilon raised to the D. So here D, this D might be different than for any particular point X. So it's sort of the average for the attractor. The correlation dimension takes into account the density of points on an attractor. And so it's going to differ from the box counting dimension, which weights all the occupied boxes equally. So if we were to calculate, say for the Lorenz attractor, a box counting versus this correlation dimension, we may get something different. People prefer, for attractors, the correlation dimension, right? And how would we get at this? You could plot log of C versus log of epsilon. So natural log C versus natural log epsilon. So you would get something like this. You might find that for really small epsilon, it's not doing much. And then it seems to rise, and then it kind of saturates out. So you take this part where it seems to be the most linear, and you take that slope. So this slope is what we call D. So you can computationally find this. The curve saturates at large epsilon because the epsilon balls will then engulf the whole attractor. And so n epsilon can't grow any further. And at extremely small epsilon, the only point in each epsilon ball is just the point x itself. You have to have points x on the attractor. So we look in this sort of middle region. So this was done for the Lorenz system. So for the Lorenz attractor at the values that we have talked about a lot, R equals 28, sigma equals 10, B equals 8/3. This has been calculated, and I'll show you the calculation. We're showing the same thing, and they're plotting, this is plotting the slope. So you see for the slope looks pretty good, and they found a slope of about 2.05. So that Lorenz attractor has, we might write it this way, a correlation dimension of something between 2 and between 3, right? We expected it couldn't be 3. If you recall, volume contraction in the Lorenz equations meant that things could not be a full measure. They could not have dimension 3. So it had to go down. And we were thinking in terms of, well, maybe it had to be a point or a limit cycle or something two-dimensional. Well, it just has to be something less than 3. In this case, it's closer to 2. It looks, when you visually look at it, it looks like it's this weird twisted surface, or what Lorenz called an infinite complex of surfaces. It's almost 2D, but this would fit with our intuition once you accept this idea of fractals, that it's between 2 and 3. So that was kind of cool. Yeah, so there's these tools for calculating things. I could mention in the last couple of minutes, one of the main self-similar things that we've stared at, the bifurcation diagram of the logistic map, just trying to calculate the dimension of the fractal set that results from the logistic map bifurcation diagram. This is a part of the image. Remember, x points on the attractor as a function of the parameter r, and we want to know at r equals r infinity, what's the dimension of that fractal? And maybe it's not obvious to you that there is going to be some kind of fractal. So what I'm highlighting here, this is showing some typical 2 to the n cycles for small values of n. In fact, these are like the super cycles, let's say. And if you were to look at the sequence of points, so we're constructing what this fractal is. We've got a single point, and then later we've got 2 points, another value of r, 2 more around each of those 2, and then 2 more around each of those 2, right? And it just goes on and on as r goes to r infinity. And then we've got, I don't know what it looks like, some collection of points. Well, you can compute it. You can compute it using the correlation dimension and just do it computationally. So this is r infinity. If you view these points as a subset of the line, it's kind of like a Cantor set. We keep removing things, but it's just made up of a bunch of points. So does it even have a dimension? And it seems like it does. So some people calculated this in the early 1980s. So it does converge. So it's going to be something between 0 and 1. Remember, you plot log of epsilon on the horizontal axis, and then log of the correlation on the vertical axis, and then look at the slope. So in this case, you get this result of, it's got a dimension of about 1/2. So a correlation dimension of almost precisely 1/2 seems odd. I mean, I don't know how to interpret that. Is that significant that it's close to the fraction 1/2? I don't know. I mean, they do get plus or minus something, but it's like plus or minus 1%. So that's interesting. Well, I thought this was kind of funny. When I don't know how to propagate my error correctly, I just put error bars on my error bars. This is not what error propagation is. If you've taken any course in that, it's not what it is. But it looks good. It's like a little fractal thing. I didn't know about this until just a couple of days ago, but the double pendulum there's a physicist has this paper just modeling, well, you can model the double pendulum and look at how many, I think it's starting from rest. You've got these two angles, theta 1 and theta 2, right? For starting from rest, count how many times or how long it takes for this thing to flip over. And then you could represent it as a fractal. Yeah, these colors indicate how long it takes for the double pendulum to flip over. And so this is representing the torus in terms of that kind of unfolding it into the two angles, so theta 1 and theta 2. And I was interested in knowing, what does this look like on the torus? So this just wraps that thing onto the torus, right? One of these angles is theta 1, the other is theta 2, but you can just kind of see it. I don't think this will let me do anything. It won't let me. I hadn't seen a fractal on anything other than the plane. This is a fractal on torus. I thought that was neat. We haven't said much about Poincare maps in things like orbital dynamics or 2 degree of freedom systems, but you get these things called islands. They're islands of quasi-periodicity in the chaotic sea. But if you zoom in on each little island, so this is that island, and surrounding this island are a bunch of little islands. If you zoom in on that island, well, then you get this island surrounded by a bunch of little islands. And oh, hey, look at one of the islands surrounding it. You zoom in, and then you could just keep on doing that. You need good numerics to do this, because we're getting at smaller and smaller scales, but it definitely shows that even in systems that come from a mechanical system that conserves energy, you've got self-similarity. So you don't need dissipation. You don't need energy dissipation. You don't need the volume of phase space shrinking to get this. I don't know if for these systems, if people have bothered to actually calculate one of these fractal dimensions. Probably that they have, but you see these things all over the place. All right, I think maybe I'll show this and we could just stop there. So I think I'll make more of a connection with the motion on attractors next time. If you ask me where this comes from, I don't have an answer. I'm not. It's the Mandelbrot set. I don't know. Or the Julia set or something. It's just the cool one that everyone thinks about.